So what we just did was rather ad hoc. We sort of looked at the truth tables and guessed what gate fit in. And this worked pretty well for simple truth tables, but obviously isn't going to scale up to large, complicated truth tables. So what we want is a more systematic way to do this, so we can always find the right gates no matter how complicated the truth table is. And in particular, we'd like to be able to find the fewest gates for a particular truth table. And this is important because the fewer gates means you use up less area on the chip and your circuit runs faster. So what we're going to talk about is a technique to do this called Karnaugh maps. And these are simply a special way of writing out truth tables so we can easily identify logic gates. And in particular, what we're going to do is we're going to order the inputs so we can circle all the ones in the truth table and write down the gate from the circled ones. Now, if you look at what people really do when they design logic these days, well, everything's done by a computer. People write their logic functions in high-level languages such as VHDL or Verilog, and then the compiler converts them to gates. It's only for the most performance-critical parts of a chip where people do this by hand. So let's do an introduction to Karnaugh maps. There are 3 basic steps here, and let's get started. So the first step is to write the inputs across the top and side. So here's sum from our half adder before, and you can see I wrote the B input across the top and the A input down the side. And here's carry. Again, I wrote the B input across the top and the A input down the side. Inside the Karnaugh maps, I've filled in the 1s and 0s from the truth table corresponding to the inputs across the top and bottom. Now the second step is circle the largest power of 2 blocks of 1s. So power of 2 means I can circle 1, 2, 4, 8, or 16 ones, but I can't circle 3 ones. So for carry, this is the largest power of 2 block. It's the only power of 2 block, and there's 1 value in it. Step 3, write down the equation. So there's the equation. This is C equals A and B. Now how did I get that? So to understand that, look at what the rows and columns mean. So this column is where B is 1, where B is true. So everything in this column has B. This row here is where A is 1, or A is true. So everything in this row has A. So the intersection of these, where that orange box is where we have both B and A being true. So that's B and A, or A and B. If we look at sum, it's a little bit more complicated. This is this diagonal pattern, and that's just XOR. Let's take a look at another example. So I'm going to start out the same way. First, I'm going to write the inputs across the top and the side. So here's my function. I've got B across the top and A down the side, and I've filled in my truth table in the middle. Now I'm going to circle the largest power of 2 block of 1s, which is this one here, and now I'm going to write down the equation. So to write down the equation, we're going to look at the same thing we did before, what each of the row and columns mean. So this is the column for B being true. This is the row for A being true. This column here is for B being false, or not B, and this row is for A being false, or not A. So our box here is at the intersection of the row where A is true and where B is false. So what that says is the equation here is A and not B, because it's the intersection of the not B column and the A row. So let's take a look at another example here. Here we have 3 1s in this Karnaugh map. So we can put in 3 circles to cover them. Remember, we can't have a circle of the size 3 because it's not a power of 2. And so what values do we have in here? Well, let's take a look at this one. This is in the B column and the not A row. So this term, or this element here, is going to be and not A. We've already seen the other 2. This one here is in the B column and the A row, so this is B and A. And this one here is in the not B column and the A row, so it's not B and A. So that tells us what our function is. Our function is the OR of all 3 of these, because it can be any one of these. So it's not A or B, not A and B, or not A and, it's A and not B, or A and B, or not A and B. And this looks complicated, and it is complicated. If we take the logic equations that we had before earlier in the class, you can go through a few steps and you can reduce this down to something nice and simple, which is A or B. So the logic equation that we have for this Karnaugh map is just A or B. Because we circled very small little blocks in there, we got a complicated equation. So keep this in mind. This is why you want to circle the largest things possible. When you circle small blocks, you get many of these terms which result in a complex equation. Let's take a look at another way to do this. We're going to circle larger blocks. So this time we're going to circle this power of 2 block. So there are 2 in it, so it's a power of 2. And what is the equation for that? Well, this is simply the row where A is true. So that's true whenever A is true. So that's A. Here's another power of 2 block with 2 in it. And what's the equation for this? Well, this is the column where B is true. So this one is simply B. And by circling these larger blocks, we get our equation immediately. We see it's just A or B, one or the other of those. So selecting larger blocks is good. You get fewer terms and a simpler equation. We can also do this the opposite way around. So we can select zeros instead of 1. So if I select this 0, what do I get? Well, this is not B and not A, so this is not B and not A. But since I selected zeros and not 1s, I now get not F equals not A and not B. And this should look a lot like the De Morgan's law we saw earlier. In fact, I can translate this using De Morgan's law to just tell me this is A or B. And I get the same thing I had before. So you can circle zeros, but then you get the inverse function. So in general, you want to circle the largest blocks. We saw if we circle these three small blocks, we get a bunch of equations and we have to work our way through to reduce it to the simple equation. If we circle larger blocks instead, we can directly get the equation, and we can also do strange things like circle the 0, but if we circle the zeros, we have to convert from not F back to F. So when you're doing Karnaugh maps, you want to select the largest power of 2 blocks to get the simplest equations.